The first thing is independence of random variables. Independence of random variables. RV I use for random variables. So what is independence of random variables? So you have discussed in the last class also, when there are two or more than two random variables, we may not always have only one random variable. So we discussed the joint, marginal and conditional probabilities for two or more than two random variables, and continuing that we'll discuss the independence of two or more than two random variables. So what does that mean? This means that the outcome of one random variable does not impact the outcome of other random variable. For example, so this is, I'll write it down, means that outcome of one random variable does not impact the outcome of another random variable. And let's write all the formulae. We know this. Okay, let's write all the formulae for each of the cases. For the CDF, that is cumulative distribution function, PMF, PDF, expectation, variance. So all these things, I'll just write the formulas so that you know formally that in case of two random variables, what should be the, how do we identify whether two random variables are independent or not. So first of all, let me write for the CDF case. So for CDF, we will have, so it's simple. So we know from the past that in the case of events, right? So the formula will be in the similar lines. So let me write it down in case of this. So for, if you write fxy, x comma y, this capital F is for the CDF. This is the symbol. This is equal to f of x into f of y, y of y. So the combined, okay, joint probability is the product of the probabilities. Then this is these two variables x and y are independent. So this is in context of x and y. Okay, so if now CDF is there, so next is like, for example, PDF. Let's see the PMF, the discrete case. So this is for discrete. So these are simple formula, you will know this. So this will be probability of x comma y given xy is equal to probability of x into probability of y. This is at that particular point, what is the probability? If these two are, that is the product, then these two variables x and y are independent. Okay, so let me write one more generic form of this also. So it can be, as I said, it can be more than two random variables also. So this can be, you can generalize this and write that f of x1, x2, so on till xn, and this will be x1, x2, so on till xn. This is equal to product of I equal to 1 to n fxi of xi. So this symbol pi, earlier we saw sigma, this was summation. Okay, this is for product. This is equal to, like, this means that this is equal to fx1 of x1 into fx2 of x2 and so on till fxn of xn, like that. Okay, this is what this means. This is product, this pi symbol. Okay, discrete case, this will be product of x and y is individual products because there is nothing common. The outcome of one doesn't impact the other. Let me write for the PDF also. The PDF would be, what will be the PDF? I'm just writing it in the symbolic format. So this will be, this is small f, right? F of x comma y is x comma y. This is fx of x into fy of y. Okay, so this is a continuous case. This are written discrete. And now expectation. So in terms of expectation, let me move to the next page itself. So if we have expectation, similarly expectation will be expectation of x comma y, or It's written xy, not like that. Xy is equal to expectation of x into expectation of y. Okay. Then we'll use this to generalize. So generally, so we'll discuss variance also. For in general, so a general formula for variance of two variables is, what is it? So generally we say variance of x plus y, if the summation is there, right? So that is variance of x plus variance of y plus 2 into covariance of, we have seen covariance of x comma y. We have seen covariance in the past, in the last classes. I'll put the link if you don't remember. So what we know about the covariance? Covariance we know already. Covariance of x comma y is equal to expectation of xy minus expectation of x into expectation of y. Okay. But for independence, we know if this is independent, these two terms are equal. So what does this mean? This implies covariance of x comma y will be 0 for independent RVs x comma y, because expectation of xy and expectation of x into xy, this is both are equal, so this will become 0. That's what I'm saying here. And if this becomes 0, what will be this formula? This term will become 0. So what will be the variance formula for independent case? So for independent, RVs, random variables x comma y, variance of x plus y is equal to variance of x plus variance of y. Okay, here's the formula. This is there, this is there, this is there, and then these two. Okay, simple products. And there's one small twist in this, because this has become covariance is 0. We know that from the past also, we have discussed this. Okay, so these are the formulas. So let's understand this with a simple example also quickly. Say for example, if the setup is, I toss a coin and I roll a die. Okay, this we have seen this example 1. Toss a coin and roll a die. So will these two random variables be independent? So what will be the for x is equal to, let me formulate, 1 if head and 0 if tail. So this is for the toss, and y will be all the outcomes, right? Y will belong to all the outcomes. This is how we write it. Y will belong to all the outcomes of the die when we roll a die. Okay, so what's next? So what will be the all possible outcomes? So here you can clearly see that both the random variables are independent. If I get a heads, it doesn't impact whether I get a 2 or a 3 or a 5 if I roll a die. So these two are independent. What will be the outcomes? So generally all the possible outcomes will be, we'll get a head and 1, head and 2, like this till head and 6. This is 1, and then either we'll get tail and 1, tail and 2, and till tail and 6. So these are the possible 12 outcomes. 2 into 6, 2 from here, 6 from here. This will be 12. So these are possible outcomes. And here obviously x and y are independent. So this is a case of independent, because we can write x into y. Expectation of x is expectation of x into expectation of y. Let me give you one more concrete example. I'll give you many examples so that it's very, very clear. Okay. So I'll give the second example. So with this you will understand a bit better. So this time the setup is toss a coin twice. Toss a coin twice. So what will be the possible outcomes here? Head head, head tail, tail head, and tail tail. And now we count the, so now how am I defining my random variables? So let's define x is equal to number of heads and y is equal to number of tails. So what will be this? This will be either 0 or 1 or 2, and similarly this will be 0, 1, 2. Okay. So now if you see, are x and y independent here? If I know that I have got 0 heads, then can I tell that I have got 2 heads? So these two events are, or these two random variables are mutually exclusive. They are not independent. So x and y are not independent. So this is some intuitive example. Then we'll apply the formula also. Simple examples, right? So let's do a problem where we will apply a formula. So for example, say for example 3. So let's consider a uniform random variable. So let's see, we have a uniform random variable. Okay, this is 0. And say it is coming from -1 to 1. So my range here is so -1 to 1. This is my b equal to 1 and a is equal to -1. This is my range. So if this is -1, this is 1, what will be this value? We know that from the PDF formula this area should be 1 complete. So this is your PDF, right? So this area should be 1. This complete length is -0 to -1. This is 1 unit. This is 1 unit. So 1 plus 1. This is total is 2 units. I'll use a different color. So this total length from here to here is 2 units. So if this is 2, area is equal to 1. So what should be this value? So this will become half. 2 into half is equal to 1. The complete area. The complete area of this rectangle. The length is 2, so the rest should be height. And this is my uniform PDF, that x is equal to half. So you remember, so what will be the expected value here? Expected value will be 0. So let's write it down. So this is a uniform distribution. Uniform distribution. B is equal to 1, A is equal to -1 from B to A. So expected value of x is equal to mean is equal to B plus A by 2, that is equal to 1 minus 1 plus -1. 1 plus -1 by 2, that will be 0. Okay, so how will we write fx of x is equal to 1 by b minus a, that is equal to half for -1 less than equal to x less than equal to 1, 0 otherwise. So this is my uniform distribution. Okay, so this is my x. So this is about x, and let's define another random variable. So there is another random variable y is equal to 2x. This is my x and this is my y is equal to 2x. So let's compute what will be this value, the expected value of xy, whether it's equal to expected value of x into expected value of y or not. So what will be the expected value of xy? Let's compute the LHS first. Xy is equal to 2 times expected value of x into y is 2x. I have defined it this way. Is equal to expected value of 2x square. How do we define sorry, how is expectation defined? Let me just check. So expectation of x is defined as, this 2 is constant, so this will come out. So this can be written as 2 into expectation of x square. This is expectation of 2 or a constant value is the number itself. So that's why I have brought it outside. It will be 2 times expectation of x is minus 1 to 1. So I'll put it into fx, that is x into fx. It is x into fx of x for PDFs. This is the PDF of fx of x. So what is the PDF? We have seen this. This is e minus a, that is half. So this is equal to 2 times minus 1 to 1, that's the range. X into half dx. Fx of x is defined as minus 1 to 1. In this range, minus 1 to 1, this is defined as half. It's 0 otherwise, so remaining things become 0 anyways. So this will become 2 into half, and this will become, sorry, this is x square, right? So this will become x square. This is x square dx. So expectation of x is x into, expectation of x is x into fx. Expectation of x square, here we have x square, right? So x square would be x square into fx of x dx. This is my PDF. If not, revise the expectation class. Okay, I'll put the link in the description. So let's carry it forward. What will be the value? This will be 2 into half. This is 1, so this goes off anyways. And the remaining thing is integral of x square dx. Integral of x square dx is x cubed by 3. And what is the range? Minus 1 to 1. This will be 1 by 3. I bring it out. X cube, that now I'll put upper limit. 1 cube minus of minus 1 cube. This is equal to 1 by 3 into 1 cube is 1, and this is minus of minus 1. That is equal to 2 by 3. So expected value of xy is equal to 2 by 3. Okay. And what will be the expected value of x? This is 0. What will be the expected value of y? This is equal to expected value of 2x, because y is equal to 2x. So this will be 2 times expected value of x, that is equal to 0. So this implies expected value of x into expected value of y is equal to 0 into 0, that is equal to 0. This is 0. This is 2 by 3. This implies that expected value of xy is not equal to expected value of x into expected value of y. This is not equal to, this is 2 by 3, because 2 by 3 is not equal to 0. Hence, x and y are not independent. We can see it clearly from here. Y is equal to 2x. There is a clear relation. Y is 2 times of x. So this is related. These are not independent. If x changes, y will change. So there is a clear relation here. But we have proved this mathematically also, that x and y, if they are using their expected value, that if they are not equal, this means that they are not independent. But there is one more thing, that, so there is a note. Okay, if expected value of xy is equal to expected value of x into expected value of y, then we cannot say for sure that x and y are independent. The inverse is not true. We cannot say that x and y are independent. I'll give you an example to show this. So for independence case, we told that expectation of x, y together, the joint probability, if it is equal to expected value of x into expected value of y, then they are independent. Okay, but if this holds, the reverse, if this holds, then we cannot say that the inverse is true. If this is true, we cannot say that x and y are independent. Let me give you an example so that it becomes clear. What am I saying? For example, let's continue with the same example. Okay, so we have a uniform distribution. Okay, let me make it smaller. Okay, so this is how, if for example 4, so this is how my x is defined. This is x, this is equal to x. So my x is a uniform random variable that is defined from -1 to 1 and whose expected value is 0. And now I define another variable z that is equal to, say, x square. Okay, so what will be the expected value of z, or sorry, this will be, now for example, so what will be the expected value of xz? Now we have to prove that expected value of xz, if this is equal to expected value of x into expected value of z or not. We have to find this out. So let's do the LHS first. Expected value of xz, this is equal to expected value of x into x square, that is expected value of x cube. What will be the expected value of x cube? Integral for this uniform case, this is defined from -1 to 1, so that will be, this is a PDF, a continuous random variable. So -1 to 1 x cube f of x dx. What is f of x? This is equal to half. You have seen this. This is the PDF here. So this is a constant uniform, half of the probability of having all the values in this range is half. So this is equal to half integral -1 into x cube into half dx. So I'll bring this half outside. This is a constant, -1 to 1 x cube dx. So what is the integral of x cube? Increase the power by 1 and divide it by the same number. So that is half 1 into, this will become x power 4 by 4 -1 to 1. So this will be, it's equal to 1 by 8 into x to the power 4, and this will be integrated from -1 to 1. So it will be 1 by 8 into 1 to the power 4 minus 1 to the power 4 minus 1 to the power 4 minus 1 to the power 4 will become 1 again. So this will become equal to 0. And what is expected value of x? This is 0. So what will be the expected value of x square? This will be again 0. Okay, x into x. So this is equal to your, x square. We know that this expected value of z is equal to 0. This is because this is the expected value of x square. Okay, so this implies expected value of x into expected value of z is equal to 0 into 0, that is equal to 0. So now you see here that this is 0 here and even this is 0. Both are same. But we have seen here that z is equal to x square. Z is directly related to x. If x changes, z changes directly in the square proportion. So we know that z is dependent on x. Although this formula is holding here, although e to the expectation of xz is equal to expectation of x into expectation of z, this holds, but even then, but x and z are not independent because clearly z is dependent on x. I hope independence is clear now. We have seen enough formulae. So now let's move to the next topic. I want to discuss independence before I.I.D. So what is I.I.D? Now let's understand I.I.D. I.I.D. So this is an abbreviation. This means independent and identically distributed. Independent, we know each sample is independent. Okay, so the value of one sample does not impact the value of other. So with this we know each sample is independent. And identically distributed means that all the samples are coming from the same distribution. Each sample comes from same distribution. Say for example, either it's like Gaussian or normal, whatever, or Bernoulli, Poisson, geometric, whatever, name it. There are like thousands of distributions, at least hundreds. Okay, so this is generally used when do we use? You must be listening to this I.I.D. Wherever in machine learning you will see that the data set, the data is I.I.D. So you will listen to this in I.I.D. assumption, that the assumption is the data is I.I.D. So in that context you will listen I.I.D, and that means that each sample is independent. For example, if I have a data set that has the height of people, okay, height of people in a city or something, okay, so the sample of heights, so each height here, so what does independence means? Independence term means that each height in that sample is independent of the other height. The height of one person does not impact the height of other person. So that is independent. Identically distributed means all these heights are coming from the same distribution, that is a normal distribution or a Gaussian distribution. So that's what I.I.D. means. I hope I.I.D. is clear.